Okay, so what we're going to look at here is how we can substitute a pronumeral for the value of a number. Now that means that the same algebraic expression or formula can have any number of values substituted into it and therefore create a variety of different values as well. So we're going to look at 4 examples with this and we're going to use a table of values as well to help us calculate these different expressions and formula. So we're going to start off here with t equals 4w. Now from the previous work that we've just done on algebraic expressions and simplifying expressions, we know that t is equal to 4 times w. So when we see this 4w written together, that means that it's 4 times w. And we're going to use this now to calculate the value of t based on the value of w. And you can see in this table just down below here that we've got 6 different values for w that we can substitute into that expression, or into that formula, and therefore find the value of t. So we're going to start off with w is equal to 1, and we're going to substitute that into our expression. So if we've got t equals 4w, if w is equal to 1, then that means that t is equal to 4 times 1, which in this case is 4. We can do the same thing when w is equal to 2. So this time we end up with t equals 4. Now it's times by w, so in this case when w is 2, it's times by 2. 4 times 2 equals 8. Now we don't need to keep showing our working out for this. We can continue to do these in our head. So when w is equal to 3, so if we're dealing with this one here, if w is equal to 3, 4 times 3 is 12. When w is equal to 4, we've got 4 times 4 is 16. Now we do have a pattern going up here, but that pattern's because our w's are increasing by 1 every time. And if we look at the next one, this time we've actually got w is equal to 10. So again we can say, well, t is equal to 4 lots of w, 4 times w. So in this case, when w is equal to 10, it's 4 times 10, which is 40. And the last one here, when w is equal to 15, we've got 4 times 15, which is 60. So you can see that whilst we've got one formula here up at the top, which is t equals 4w, depending on the value of w that we substitute into that formula, we can get a variety of different values for t. So it's all dependent on that value of w. Now we're going to look at a slightly different example here. Notice we've changed the variables here. We're now using p and f. It doesn't matter what variables we use, the same rules apply. And again, we can let f and p be any number that we want them to be. So again, in the table here, I've got 6 different values for f: 1, 2, 3, 5, 10, and 100. And we can evaluate p for every single value of f that we've got there. So again, if we show some working out for the first few, so p equals 3f minus 2. So using f is equal to 1, we end up with p equals 3 times 1, because again 3f means 3 times f, minus 2. Now a little bit of BODMAS here, do the multiplication first, so 3 times 1 is 3, minus 2, 3 minus 2 is 1. So that means when f is equal to 1, p is also equal to 1. We can do the same now if we show some working out for when f is 2. So again we've got p equals 3f minus 2. So if f equals 2, we get p equals 3 lots of f. So 3 times 2 minus 2. 3 times 2 is 6, minus 2 is 4. So this time we get p is equal to 4. We can now continue working this through. So when f is 3, we've got 3 times 3 is 9, minus 2 is 7. When f is 5, we get p equals 3 lots of f, so 3 lots of 5 is 15, minus 2 is 13. When f is equal to 10, we get 3 times 10, which is 30, minus 2, which is 28. And the last one, when f is equal to 100, this time 3 times f, so 3 times 100 is 300, minus 2 is 98. Now, what we're going to do with the next two is just a little bit more complicated going through. This one we've got a squared term, so this time we've got x equals m squared minus 1, and again we've just got 6 different values we're going to look at. We need to take a little bit more care here with this because we are dealing with squared terms. So again, we're just going to work through the first two by showing some working out. So if we've got x equals m squared minus 1, this time our first value is m equals 0. So we have m equals 0. That means we've got x equals. Now, to make it a little easier, I'm going to put this in brackets because we're involving a power next to the m. So we'll put 0 in brackets squared minus 1. Now, 0 squared is 0, and 0 minus 1. A little bit of directed number here. 0 minus 1 is minus 1. So in there, we put minus 1. So that means that x is equal to minus 1 when m is 0. Now, if we let m equal 2, so again, we'll work through this. So m is equal to 2. That means x equals, this time, 2 squared minus 1. 2 squared is 4, minus 1 gives us 3. So that means when m is equal to 2, x is equal to 3. Now we can go through and work these out for the rest of them. So when m is 4, we get 4 squared is 16, minus 1 is 15. When m is 5, 5 squared is 25, minus 1 is 24. When m is 10, we get this time 10 squared, which is 100. Minus 1 is 99, and the last one there is 12 squared is 144, minus 1 is 143. Now, you might be wondering why we use brackets down here, and we're going to go a few steps ahead really of where we are at the minute, but just to show you what would happen when m is negative. So let's say that m equals minus 3. So that means if we use the same formula, x equals m squared minus 1, we get x equals. Now, because we've got a negative, this is where the brackets become important. So we put the minus 3 in a bracket squared minus 1, and then we can see that it's minus 3 squared. So minus 3 times minus 3, negative times a negative is a positive. So we end up with 9 minus 1, and 9 minus 1 is 8. So it's important that, because if we have to deal with some negative numbers later on, then we need to make sure we're using brackets. So we're effectively calculating any values that involve negative numbers. Now, this last one is different again, and you'll notice how this is different to the one involving the p and f before. We had p equals 3f minus 2. This time though, it's f equals 5 minus 4p. So the variable term doesn't come first here. And we need to take a bit more care now when we're calculating this. So we're going to calculate this here. Again, we've got a table of values. We're going to work this out for p is equal to 0. So when p is 0, we've got f equals 5 minus 4p. So again, we get f equals 5 minus, we're going to substitute in the 0 for p. So if we work this out, now again, BODMAS means we work out the multiplication first. So 5 minus 4 times 0 is 0, so 5 minus 0 is 5. If we then go ahead and work this out, let's jump ahead and do this for 3. So we're going to say that when p is equal to 3, we have f equals 5 minus 4 times 3, so times by 3. Again, bit of BODMAS here, 4 times 3 first, so 5 minus 12. Now, we're going to go into negative numbers here. 5 minus 12 is minus 7. So that means when p is equal to 3, f is equal to minus 7. So we'll go back and work these out for when p is equal to 1. So when p is equal to 1, 4p is 4. So 5 minus 4 is 1. And when p is equal to 2, we get that 4p is 8. 5 minus 8 is minus 3. When p is equal to 4, we get 4p is 16. 5 minus 16 is minus 11. And the last one, when p is equal to 10, so we'll just go over this one here. So when p is equal to 10, got that f equals 5 minus 4 times 10. 4 times 10 is 40, so this becomes 5 minus 40, and 5 minus 40 is minus 35. So we can see here we're combining together substitution, so we're substituting in different values for variables, and again each variable, as you notice, doesn't just represent one number. You can see here that p can represent any single number that we substitute in, and then we get a corresponding f value from it, and that was the same with each formula we substituted into. There is always an unlimited and infinite number of values we can sub in for a variable, and we end up with a corresponding variable at the end of it after we've completed that substitution.